Good afternoon, everybody. Thank you for attending, and thank you to the organizing committee for inviting me to speak. My presentation today will be on a sediment velocity model that we developed to improve the simulation of basic amplification effect in Southern California. This work was supported by the Southern California Earthquake Center, and it was done in collaboration with my former PhD student, Jashi, and Dr. Elmaz Seilabi from the University of Nevada, Reno. So if the purpose of our seismological models and the intent of the engineering community to use the simulations from the seismological models is to increase the resolution of our groundwater simulation in the high frequencies, these high frequencies can see the soil. And so the nonlinear heterogeneous and isotropic three-dimensional crust that forms that affects the propagation of seismic waves and ultimately the amplification of seismic waves and the way that these are transmitted to the structures cannot be captured by one-dimensional correction factors. And not only that, but if we go one step further and we look for simulations of events yet to happen, really large events, this shallow crust creates the conditions or imposes constraints of very large ground motions during very large earthquakes. So we want it to be 3D, and we wanted to have the geometry and the heterogeneity that is appropriate in order to understand the limitations of these formations to transmit high frequencies. So the shallow crust matters to engineers, and it will significantly modify the high frequencies that we're trying to propagate. And so that has motivated us to look into improving the poorly resolved shallow crustal models that we have by using data-driven applications. The Southern California Earthquake Center geotechnical layer is shown here. It's a smooth geometrical function that is a function of the shear wave velocity, the average shear velocity of the top 30 meters, known as VS30. The geometric function fits the VS30 in the near surface and then successively connects with the community velocity models at 350 meters depth. The depth is fixed, and therefore the prescribed connection between this geometric function of the subsurface velocity at 350 meters can mask impedance contrast and alter basing edge geometries. So that would lead to the deterioration of ground surface predictions compared to the community velocity models without any geotechnical layer whatsoever. So we thought that the idea was to evaluate, Ricardo Taborda has done a bit of work on this problem, try to evaluate the geotechnical layer. That has led us to understand that sometimes it leads to worse predictions than ignoring it altogether. And the next step was, how can we make it better by trying to understand what it is that, how do we fill those basins and also respect the boundaries of the basin edges. So the sediment velocity model is an idealized model derived from observations measured for VS profiles in quaternary sites around California. It's a function of available physical properties, VS30 and Z1000, and it's designed to preserve the basin geometry while refining the stratigraphy inside the basin. This is the databases that we have used. It was approximately 1,000 profiles, although these days the UCLA group has improved even one step further the profile database, and we could go back and increase the number of profiles on the basis of which we have derived this model. The approach was we used we used data to bin the profiles, the data properties to build the profiles based on VS30. Now, the different databases were not only proprietary or non-proprietary, belonging or have been harvested by different organizations, but also they were heterogeneous in the sense that some of them were measured using invasive and others were measured using non-invasive conditions and methodologies. And one can see here what that means. If you look at there's a systematic difference between the black line, which is the AARA VS30 database by Alan, was collected by Alan Young et al. And these were non-invasive, were based on surface wave measurements, and these were able to do inversion of the layers on the near surface. Rather, the invasive databases shown in green, blue, and red. You can see here that there's a constant value in the near surface. That's where the the drill starts measuring. And we had to homogenize these databases before trying to capture the variability of the velocity profile, the statistics of the velocity profiles with depth. So the systematic difference was approached as follows. We looked at the difference between the invasive and non-invasive method as a function of depth. We realized that at depth 2.5 meters, the databases were actually consistent, and therefore we established a correction factor that made all those profiles consistent in the near surface. The model development was derived by using, the model development is as follows. The constant value in the near surface, where z star could be those 2.5 or 3 meters or 5 meters, depending on the type of data that we have. And the variation then with depth, which is an exponential function. The number of profiles that we use to derive this expression is shown here, and the parameters of this model are then based on measurable properties or available properties. In other words, are based on VS30. So you can see here the different bins of the VS30 profile. Some had more and others had less. We try to, we let the data drive the bin formation of the databases. The blue and the dashed blue are the geometric mean and standard deviation of the profiles in each bin. The red is the fit of SVM within the bin with its variance. Note that we both parameterize the median as well as the variance of the profile. So the SVM parameters are shown here. VS0 is the velocity at the surface, and this is a function of VS30, and parameters that are geometric, that are curve fit, basically the set of data. K is the constant that multiplies the depth of from that first constant layer, 2.5 meters, and then n is the 1 over n is the exponent, and the error bounds were also parameterized, idealized first and then parameterized, but also the fit of the median is shown here with a dashed line. The additional things we learned while deriving SVM were the following. We derived the variation of the soil layer thickness versus layer depth. Even if the profile derivation is smooth, we ultimately, in order to implement it in a computational model, we need to discretize. And that discretization was led by the data. There was a systematic variation of the velocity depth that doesn't necessarily come from physics. It comes from inversion, or comes from the methodologies that we use to do invasive characterization, but nonetheless, that's the information we have, that's the information we use. And we also derived the Z1000 versus VS30 for the data that we had, for the stations, for the sites that we had velocity measurements down to 1,000 meters per second, and notably the curve fit comparison of what we used for SVM with the Campbell and Pozonia CY14 relationship with Z1000 and VS30 is shown here. So how SVM works, given a VS30 and a Z1000, depth to 1 kilometer per second, the variation of the shear velocity is shown here, smoothed. We stop at Z1000 and we let whatever material properties the community velocity model has, the background has, to take over. We then discretize the SVM component using the variation of the thickness with depth. And then we can also create a stochastic realization of this variation, of this stepwise profile variation with depth, using a stochastic, using the parameterized version of the error bins. Sorry. So if you see here, if this is a cross section, it goes from Long Beach towards Pasadena, I think. I don't know where the map is. I think next one here. But if this is a cross section and we have information about VS30 and this would be it, it's crude because in some cases we use measured data, in other cases we use correlations with topography, etc., and all these are synthesized together, not necessarily homogenized properly, at least yet. And then we also have the Z1 contour. You can see here, first of all, that we fill the inside of the basin with the SVM, but then once we get to Z1000, then we let the basin take over, except in the cases where we have a very low VS30, but are zero Z1000 based on SVM. In those cases alone, in order to create a smoother variation at the edge of the basin, we actually use the Z1000 VS30 correlation that we derived that I showed you earlier. So this is actually the same profile with different colors. The VS30 not to scale and the Z1000 is shown here. A smaller, more zoomed in version. And then the bin, we can actually create stochastic variations of these by just using the parameterized variance of each one of the parameters of SVM, and also following some semi-empirical, semi-intuitive rules of how the seed number needs to change from site to site until we actually have high resolution sites or arrays. So for us to derive based on data the correlation lengths in the horizontal direction and the vertical direction, we use the Toro model for the vertical direction realization, randomization, and the horizontal direction we use constraints on differences of seed number from one realization to the next. So the SVM was validated using profiles from the Southern California Earthquake Center community velocity model with and without geotechnical layer. The validation was performed on a holdout data set of 43 profiles that were not used for training, and the validation was done on the basis of we checked the VS profile correlation, and we also checked the one-dimensional amplification. This is an example of a site with VS3440. You can see here the measured profile, which is the black one, the SVM. This is prediction on the basis of VS30. There's no curve fitting here, and CVMH with GTL. All three of them, actually the GTL in this case does a remarkably good job. And the CVMS without GTL is actually just a rock outcrop of 4 kilometers per second. And the comparison of the various amplification factors are shown here. The measured one is the black, and you can see that SVM does a fairly good job in capturing the amplification of this range. GTL introduces more amplification, higher amplification. And more variability, if you will, in the frequency range. The values that you see here are just the goodness of fit based on the cross correlation between the L2 norm difference between the profile or the amplification factor and the measurements. Another profiled example is here, VS37 660 meters per second. The measured profile is the black. The yellow is SVM, and now CVMS and CVMH with GTL are closer together, but they are further apart from the near surface measurements of near surface predictions of SVM, and this is reflected in the transfer function, analytical transfer function. And this is just a cumulative description of the goodness of fit. Vertical axis is the number of sites, and the horizontal is the goodness of fit of the VS profile defined here, the error function, and also the goodness of fit of the amplification factor, again as the error function, so that we can have we can use it to evaluate whether we over predict or under predict, and you can see that the SVM systematically provides the better results compared to CVMS as well as CVMH with GTL compared to the measurements. And a different way to see the variability, the variation is these violin profiles, violin graphs. And you can see here the GTL has a very large variance, and the median is around 4.5 goodness of fit of the profile, as well as the transfer function. The transfer functions of SVM are narrow, have a narrower variance, and they also have a slightly higher median. But the profiles themselves are significantly better than either the community velocity model or the community velocity models with geotechnical layer. Last but not least, this is fresh out of the oven, a simulation that we did to prove the pudding. The Borrego Springs magnitude 5.4. surface velocity of CVMS with the GTL is shown on the right, and then the corresponding, the same one with SVM. We have implemented, with the help of the SCEC-IT group, implemented the SVM in the Southern California Network Center community velocity model, so we can query and we can generate three-dimensional finite element meshes using SVM as well, the same way as we do using GTL. And so we ran a relatively small event. Two examples of cross sections of how GTL and SVM vary. You can see here in the X direction along the 20 kilometers from the edge of our model. This is the main difference that I was trying to point out earlier. We have no information besides this point from the community velocity model. So we basically just fill the shallow crust to merge the information that we have from VS30 with the information we have from the Southern California velocity model. GTL, on the other hand, so long as there is a VS30, the profile has to match at 350 meters per second, 350 meters depth, and you can see this alters this basin edge. Similarly here, we have some discontinuities, mostly coming from the fact that some VS30s are actually, or profiles, some VS30s are actually measured, whereas others are inferred. And this profile, this data set has not been yet fully homogenized. And as a consequence, you see, as soon as we have a discontinuity here, SVM just blends this with the surrounding. With the case of the GTL, the discontinuity is stretched down to 350 meters to conform to the geotechnical constraints, to the geometry constraints. And first set of results are encouraging. These are velocity time series. This is a systematic observation that we've seen, although we haven't compared. This happened 2 days ago, so we haven't compared the velocity. But Grand Valley Downhole Array is a reliable site, and SVM compared very well with site characterization measurements in that location. And you can see both X and the Y direction, horizontal, both components. SVM produces high reverberations. There's no damping, there's no Q differences in this case. It's just purely because of the variation in the model. With depth, as well as the fact that if there is an impedance contrast between SVM and Z1000, we leave it there. And so this amplification here in the white direction is purely because there is discontinuity in the profile, and we don't overrule this discontinuity. So for future work, we want to implement the same process in a dense array site. So we can start coupling SVM with spatial statistics that are data-driven. No seed number empirical models or even Toro models that come from a much wider range of sites and site conditions and areas. We also want to test for a larger region, and a scenario simulation is a little stronger. So we start introducing nonlinearities, but first we have to do the statistics of the comparison with the profiles. We are, however, encouraged by the fact that systematically we see that SVM reverberations are stronger, and that they, at least visually in the stations that we were able to pull out between now and 2 days ago and now, we have been able to see good comparison. We have a USGS proposal pending to the Northern California USGS in collaboration again with Professor Nassel Lavi. The purpose for us to transfer the framework to Northern California, try to improve the sediment velocity model for this area, and then also do validation with regional motion simulations. The bottom line of the presentation, we need to synthesize high resolution crustal models if we are targeting high frequency. So it's not only to improve our seismological models. Of course, it's very important to improve the source models. And I'm sure that once we move to dynamic rapture, those high frequencies are going to be more systematically generated, and we'll have some physics from the source up. But the important thing is that if we target in high resolution, we cannot do it without improving the shallow crust models. And we are encouraged by the fact that a simple one-dimensional data-driven model that is just constrained for a specific region and a certain time of sedimentary deposits in basins in California is showing promising results in terms of improving the site amplification and the profile characterization. The SVM is available on the Powerful Routines and Jupyter Notebooks here, and there is a reference. Thank you for your attention. I'll be happy. I would be happy to take questions, but since you're seeing the recording, probably I am not here. So please email me